welcome to the Journey Shake Chem. I'm so excited today. You know how very excited I get when we're going to do lab, and this is a very exciting lab, and it's graded on accuracy, so we'll just see how accurately we can do that. We'll do the 2 warm-up questions as quickly as possible so we can go over them and get into the lab. In number 1, we are solving a problem very similarly to what we will be doing in the lab. And we are using the ideal gas law. And I know that moles, my N, is equal to grams over molecular weight. Therefore, I will substitute PV equals grams over molecular weight, RT. And again, sometimes a small lowercase m is used for grams and a capital M is used for molecular weight. However, I like to keep them very distinct, and that's why I use these letters. Now I'm solving for molecular weight, and therefore I will rearrange it algebraically, solving for molecular weight. And therefore molecular weight equals grams RT over PV. It's always good to review our algebraic rules. And I'm given 0.5 grams in the problem, and the R that I'm going to use is consistent with my kPa, and therefore it would be 8.31 kPa liters per mole Kelvin. And I'm given a temperature of 101 degrees Celsius, and that must be changed to Kelvin, and then that would be 374 Kelvin. And the pressure given in the problem is 101.3 kPa. And the volume is given in milliliters, and my constant has liters, and therefore I must change it, or else I would have to solve for my constant again using milliliters, but it's easier to just go ahead and change this. I have 280 milliliters, and 1 liter is 1,000 milliliters, and therefore this is 0.28 liters. And when I do the math, 5 grams times 8.31 equals times 374 equals divided by 101.3 equals divided by 0.28 equals. And I come up with 54.7867. Now, when we take AMUs off of the periodic chart, we take them to the tenths, and therefore molecular weight will be handled the same way. We're not following significant digit rules, and therefore this 8 rounds the 7 up, and my final answer is 54.8 grams per mole. And we can see that it comes out grams per mole if we look at how our units cancel. My kPa cancels, my Kelvin cancels, and my liters cancel, giving me grams per mole as my final unit. In the second problem, we are asked how we would determine the volume of the flask. And this is my Erlenmeyer flask, and because gases expand to take up the volume and shape of the container, we must determine the volume of the total flask. And just because it says it's a 250 milliliter flask, that's just stamped on. And different flasks can hold a different total volume, and we're going to determine that in the lab by filling this up with water and then pouring the water into a graduated cylinder, and you'll see how that works later on. And we need to do this because our volume in our equation is necessary. We need the volume of the flask. This is what we're going to be doing. We're going to determine the mass of the condensed vapor, because remember, when I put this into boiling water, its boiling point is lower than the boiling point of the water, and it will all become vapor. Well, as soon as I remove it from the heat and it's cooled down, it will condense back down into a liquid. And that's why it's called the mass of the condensed vapor. And then we know our constant. We will determine the temperature of the boiling water. We will know the barometric pressure and determine the volume of the flask and be able to determine the molecular weight of the isopropyl alcohol. And that's how we'll do that. And I can't wait to see you over in the lab. Well, here we are in the lab. I get so excited in the lab, I could just jump up and down. But I have to control myself because we must move on and do the lab. Well, the first thing I'm going to do is get the mass of a dry, clean, empty Erlenmeyer flask with a tinfoil top and a rubber band. I need the mass of it empty. And my scale is on 0. And now I get a mass of 128. 128. 128.29 grams. Now I must poke a hole in the top to allow the air to come out, and then also the air will return back in. But the liquid will become all vapor and expand to take up the whole volume of this flask. Now I'm going to poke a little hole. And it is somewhat difficult to see because it's very, very small. And now I will see you in the lab where I can use the Bunsen burner. I get so excited when I get close to using a Bunsen burner. And first though, I must get 2 to 3 milliliters of my isopropyl alcohol. And I'm going to use this container, and it has graduations on it, and I can just go ahead and get 2.5 milliliters. And because it's not an exact amount, that will be fine. And I will open up my little cap on my Erlenmeyer flask in order to pour it in. Now, oftentimes students want to get the mass, but I'm not going to get the mass until I have already put it in the boiling water and evaporated the liquid. And therefore, I'm going to go ahead and put my rubber band around it and maybe tighten it up a little bit here. Whoop. Those rubber bands, they just get away from me sometimes. Tricky little things they are. But I want it to be nice and tight. Now, I'm going to go ahead and clamp it into the beaker of water that I have set up here, and I'm going to clamp it down to make it more stable. Therefore, I'm going to first clamp it. Mechanical things. I'm not really very mechanical sometimes. And then I'm going to attach it to my ring stand and submerge it as much as I can. And be nice and tight in there. And there I have it. Now I get to do my favorite thing. I get to light the Bunsen burner, turn on the gas, light the Bunsen burner, get a little spark. Wow, that was really easy this time. Sometimes easier than others. So I put it back underneath there, and we are going to get that up to boiling. And as soon as I see there's condensation going on there on the outside of my beaker, but that's fine. And once I see bubbles in the water, I know that the isopropyl alcohol has a lower boiling point because it is a volatile liquid. And I'm going to wait 5 minutes once I see that very first bubble. In the meantime, I'm going to record the barometric pressure. And the barometric pressure today, I have my little graphing calculator that has a barometer with it. And I'm going to get the barometric pressure here. And it says that it is between 87.7 it seems to stabilize at 87.70. 87.70 kilopascal is my barometric pressure today. Now, I will see you in a few minutes as soon as the water begins to boil, and we're almost ready for that. And I'll be right back. Now, this has been boiling about 3.5 minutes, and I'm going to go ahead and get the temperature of the boiling water, because that is going to be the temperature at which the vapor has gotten to inside of this beaker. And I'm going to go ahead and take its measurement, and you can see that in the beginning it goes up quite rapidly. I don't want to touch anything in there because that would conduct some heat. We are now going 80. And I am at an elevated altitude, so the boiling point will not be 100 degrees Celsius as it is at sea level. And by the time I get this measurement of the boiling point of this water, it will be about time to remove it from the heat. And there are, of course, devices to clamp the thermometer on the ring stand. However, because I'm just getting a quick measurement here, I am not going to clamp it down, and my ring stand is not tall enough for that. We are getting quite a vigorous boil here, and therefore we'll need to turn off or lower the flame here. Not to worry. It makes it kind of exciting, doesn't it? Oh yeah, we love the excitement. And my boiling point is 96.0 degrees Celsius. 96.0 degrees Celsius. And then I'm going to turn off this Bunsen burner, unfortunately, but we have to go on with the lab. Now I'm going to remove the flask from this beaker. I'm going to stabilize the beaker while I go ahead and manipulate this clamp. I want to make sure that I'm cautious. Grab a hold of it and return it. And we know that metals conduct this heat, and they also remove it quickly, so it should relieve the heat pretty quickly. I have to loosen the clamp there, and it needs a few minutes possibly to cool it. Well, I'm going to go ahead and cool this and dry it, and it's very important to dry the tinfoil as much as possible, because any water that's left on that tinfoil that hasn't been dried off will add to my mass, and I want to get my mass as accurately as possible because this lab is graded on accuracy, and therefore I must pay particularly close attention to my technique. So I'll dry and cool this, and I'll see you at the scale. Now, here we are going to get our final mass of the Erlenmeyer with our condensed vapor, and it's all been dried off, and I'm going to get my final mass. Very, very important number here, and it is 128.80 grams. 128.80 grams. We have one more thing left to do. We must determine the volume of this flask because the gas would fill the total volume of the container, both the shape and the volume of the container. So I will see you at the lab station. Here we are at the lab station. I am going to remove the tin foil and the rubber band, and I need to get the total volume of this flask. And therefore, I am going to fill it up with this water from this beaker, and I want to fill it all the way up so that that's exactly how the gas did. It filled it all the way up. And then I'm going to pour this into this beaker and measure it from there. Now, it is true that we have a small amount of water in this graduated cylinder, but that is one of our sources of error. And hopefully, we have been diligent enough to get very good numbers. And I'm going to fill it here so that the bottom of my meniscus is on the 100, because I know that it's going to be more than 100 milliliters. And I can pour it back into this beaker because it's the total amount of the water that I want to get. And this is 100 milliliters. And now I'm going to pour it again, try to get as much of the water out as I can, and pour it one more time. And I know that it will go up to 100 milliliters again. And I need a couple more drops. Just a couple. Oop. And I'll pour a little bit out. And the bottom of my meniscus is on the 100. And therefore, I have 200 milliliters that I've done so far. And then this should be my final. Trying not to get so many bubbles in there. And here we go. We have 280, 1, 2, 3, 182.5. 85, 86, 87, 187.5 milliliters. 187.5 milliliters is the volume. Oh, 285, excuse me. 287.5 milliliters. 287.5 milliliters was the amount of water that was in this flask. And that's all the numbers that you need. And you have the formula for the isopropyl alcohol, so you can do your theoretical or calculated value. You have all the numbers that you need to determine your experimental value. And hopefully we were very close, and I have a good feeling about that. I know it will be fine. Well, thanks for being here. It was some fun. I love doing lab, and I can't wait to see you tomorrow.